Hello. So today we will study operators in a quantum theory. Okay, we will define what we mean by that, and the reason is that this lecture will be mostly algebraic or mathematical. But the reason to look at the operators is that any physical observable in quantum theory, any physical observable in quantum theory maps to operators. Okay. I mean, of course, there are more general operators which may not have anything to do with physical observables, but this is one reason. And secondly, in the next lecture, probably we will see that symmetry is also has to do with some special operators. So that's basically, in very short, that's our motivation. But let's now just study it in a very algebraic fashion. So let's say we are given a Hilbert space. Okay, and the elements of this Hilbert space, we denote in the bracket notation as alpha. Okay, so alphas belong to the Hilbert space. Okay, so this is ket vector, and I'm very sure you know that this is Dirac bracket notation. Dirac bracket notation. Okay. Now a very important thing is to define what is called a bra vector, or mathematicians will call it dual vector space. And what are they? They are just linear functional on the Kate space. So for example, if I denote a bra vector by, let's say, gamma, then what do I mean by that? Then gamma with C1 alpha plus C2 beta. So this is a linear combination of two Kate vectors. Arbitrary linear combination. Then this is same as C1 gamma alpha plus C2 gamma beta. Okay, and these are usually complex numbers. Complex. Oh. So this is gamma beta, and these are complex numbers. In general, they can be real, but they're in general complex numbers. Okay, this will be very important later, we will see. So now let's just go to what we mean by operators. Okay, so the Kate vectors also, you can see that. So the Kate vectors, so they are mapped from the Hilbert space to C numbers. Okay, what do we mean by that? It means that given a Kate, bra vector maps it to complex numbers. Okay, So they are maps, they are actually linear maps. They are linear maps from the Hilbert space to complex numbers. Okay. Now what are operators? Operators are maps from a Hilbert space to itself. Okay. So that means that if I define operator O, then an operator takes any kth vector and gives back another kth vector. Okay, so usually this is denoted as O times alpha, and this is another another vector in the Hilbert space. Okay, now so that means that first thing is addition of operators. So up to this point we have just defined this quantity O acting on alpha. So addition of operators, say let's say we have an operator O1 plus O2, and what is its action? Its action on alpha is simply O1 on alpha plus O2 on alpha. Okay, so this is the addition of operators. Similarly, you have multiplication of operators. So let's say I have multiplication of O1, O2. How to define its action? The way it's defined is that O1, O2 acting on alpha is simply same as O1 acting on O2 alpha. Okay, this is why this is confusing, because it is not at all clear what is the action of this operator, but we know this thing, and this is another some kth vector alpha tilde, some another kth vector, and given another kth vector we know what is the action of O1 alpha, right? So just from this then definition that how the operator acts on any element of the Hilbert space, you can define its action on any other, you can define addition, multiplication of all these operators. Okay, it's very important to note that O1 O2 is in general not O2 O1. Okay, so that's not necessary. Okay. Now we want to define two special type of operators. One is called linear operator. I mean, there are two types of operator. One is called linear operator and one is called antilinear operator. So what are them? A linear, so let's now take an arbitrary linear combination of kth vector C1 alpha and C2 alpha, C2 beta. Okay, so we define we denote the linear operator by U when we define the antilinear operator by V. So let's say we are given this kth vectors. Then a linear operator U acting on C1 alpha plus C2 beta is same as C1 U alpha plus C2 U beta. which means that if you know the action on any vector, then if you take if you multiply by any complex number, you also know it in this way, because C just passes through the operator U. Whereas for antilinear operator, if you take, sorry, this is V, this is V, C1 alpha plus C2 beta, and this is same as C1 star, note this star, which is just the complex conjugation, alpha plus C2 star B acting on beta. Okay, so it's very important to remember that if you multiply a vector by an arbitrary complex number, then it complex conjugates it. So when it passes through, it complex conjugates. Okay, so this is you remember this complex conjugation, and this is called antilinear operator. Okay, so these are antilinear operators. So this is linear and antilinear operators. Now the thing we want to define is that something called unitary operator. Wait. So okay. Now up to this point, okay. Wait, and define another thing. Let's define adjoint of an operator. Adjoint of an operator. So adjoint of an operator, so let's say given O, we denote adjoint of O as this way. Okay, and again the way we define adjoint of O is beta acting on O dagger alpha is same as so let's define in this way, beta acting on O dagger alpha, so that O dagger only acts on alpha. There is no, up to this point we haven't defined any action on the kets, right? So that's why we have to remember it. So adjoint of O is simply this as okay. So this is the definition. Now, important thing to remember that up to this point, we have defined action of an operator on Ket vectors. Now question is that how they act on bra vectors. Alternatively, the question is that what is the action of the operator on dual vector space. Okay, and the way it is defined is that, so let's say there is a Ket vector beta on O. So the way it's defined is that you define it again using the definition that you will okay, wait, so here we have to make a distinction actually. So the definition first defines for linear operators. So for linear operators, beta u is defined in that way. So this thing we are trying to define, this is this, okay, where yeah, so for any alpha, so we know this action because we know what is this, we know this because this is the way the action of an operator was defined. And then this from this and from the inner product, so basically from the action of the operator on Kate and from the definition of inner product, we can define the action on bra vectors. Okay, but this definition this definition only works for linear operators. Why? We will see. Let's take antilinear operator. Okay, now let's try. Let's say the definition is same. Okay, so acting on U is alpha plus beta P acting on alpha. Okay, but okay, let's take now a different combination. Let's say now given this, what about C1 alpha plus C2 gamma? What about that? Let's say beta u this B acting on C1 alpha plus C2 gamma. Then this if I had defined in this way, this will be same as this V acting on C1 alpha plus C2 gamma. And then since B anti-commutes with C, since B takes C1 to its complex conjugation, this is same as C1 star beta P acting on alpha plus C2 star beta P gamma. Okay, but this contradicts the definition of this contradicts the definition of bra vector. Why? Because bra vectors are linear operations. Bra vectors, so if you define this to be some bra vector beta tilde, let's say, then I expect beta tilde acting on this should be same as beta tilde C1. So let's see. So this should be beta tilde C1 beta tilde alpha plus C2 beta tilde gamma, which you can again using the definition show that this should be same as beta V acting on alpha plus C2 beta V acting on gamma. Okay, so that's the this is follows from the definition of bra vector. Then what's happening here? So that this is clearly contradicts the definition of bra vectors. Then the way the action of a antilinear operator on a ket is defined in the following way. So beta V alpha is same as alpha sorry, wait. Not alpha, beta V alpha star. Note this star, this is important. This means complex conjugation. Okay. This was not there. This was not there for linear operators. For linear operators, it was just this thing is same as this. But for antilinear operator, the definition from the in order to get the definition of a ket vector, we have to actually complexify when we define in the action of bra vectors. And this is a very important thing. Okay, and this also says that for linear operators. For linear operators, beta u alpha is same as beta u alpha. Okay, so that's why we never use the bracket. We usually write we never use this round brackets, because we always use this way. So left action, it doesn't matter. I mean, this quantity, whether I put the bracket in this way or whether I put the bracket in this way, is the same. But this is not true. This is not true. Not true for antilinear operators. That's why I often say that the bracket notation is not good for antilinear operator. Okay. Now we will define one last thing before concluding this lecture. We'll define unitary operator and anti-unitary operator. So unitary operator is that, let's say we have an operator u. So if it is an unitary operator, so let's say this we write in this way. U is unitary if beta u, so in the same way I can define u acting on some arbitrary vector beta to be this. Beta alpha is same as beta alpha. Okay, it means that, which means if I have dot product between two vectors, one bra and one ket, and if u works on both the bra and the ket, then it doesn't change the inner product. Now, so this is the definition of unitary operators. Now there is also something which is important for our discussion in quantum theory, is that anti-unitary operators. So let's use the same definition. Let's say I denote in this way: alpha u and beta u. Then u is anti-unitary, anti-unitary if beta u alpha u is beta alpha star, which is same as alpha beta. Okay, again it complexifies. So it actually doesn't preserve the inner product, but it actually preserves, if you compute this quantity, both unitary and anti-unitary operator preserves them. And the interpretation is clear that this is related to the probability amplitude, so we will see it later. But here the basic point is that, if you want to define anti-unitary operator, then for anti-unitary operator, beta u alpha u, beta u ket times beta u bra times alpha u ket is same as alpha bra beta ket. Okay, so there is an interchange of order. And this is important to define the anti-unitary operator. So here probably in this lecture we at least came across two things which complexifies, and antilinear operators and anti-unitary operators. Okay, so antilinear operators complexifies all the complex linear coefficients which is in front of bra vectors, ket vectors. An anti-unitary operator, it complexifies actually the inner product. The inner product becomes complex conjugate of itself under the anti-unitary operators. So then in the next lecture we will see that why these things are useful and how it becomes why we studying this.